Today we're going to be talking about nuclear physics. Okay. Now, when we talk about nuclear physics, it's important to understand what we're dealing with here. Right? So, nuclear physics is basically, the physics side of whatever really goes inside the nucleus, right? Okay. Which is something we're going to talk about. Okay, so what is the nucleus? Where does it where do we find it? Right, so I'm sure you guys know what an atom is, right? Atoms are the smallest particles that we have out there. They're very small, we can't really see them. Okay, so but yeah, within those atoms we find three things. We find electrons, we find protons, and we find neutrons. Okay, these two things here, this is what we call as the nucleus. Okay, let me show you a quick model for what an atom would look like. So here we've got a tiny model of the atom. Okay, these guys that you see, this one, these is a key, as you can see, are all revolving around this pink thing you see here. Okay, this pink thing is what we call as the nucleus. All right, this is what we call as the nucleus. Inside the nucleus we've got positively charged protons, okay, and neutrons, and these guys right here are called as electrons, which carry a negative charge. Okay, so the mass of the atom, if we talk about that is mainly concentrated over here in the center. Okay, it's mainly concentrated in the nucleus. We'll talk about why that is the case in a bit. Okay, and like I mentioned, it is surrounded by electrons which are constantly revolving in orbits around the nucleus. Okay, and the majority of the space that you see here, all of this space, see, this is just an empty space. Okay, and we also carried out an experiment after which we were able to to say that okay, the majority part of an atom is empty space. There's not much there to look at. Okay, now, but yeah, we'll talk about that experiment in a bit. It's called the Giger-Marston experiment or the Rutherford experiment. All right, we'll talk about that in a while. Now, next we have this thing called as the proton number and the nucleon number. Okay, so for the proton number, what do we mean by the proton number here? What is it? So when we talk about an element, let's say any element, okay, let's say we have an element X, right, just for the sake of it. Okay, here we will have the proton number and we're going to have your neutron number. Okay, it's going to be listed over here and some number would be listed over here. All right, now here we have the letter A, here we have the letter Z. Okay, all right, letter A here stands for the nucleon number. Okay, write that down. It's called as the nucleon number, and this Z here is what we call as the proton number. All right, so proton number here is the number of protons that you have in an atom. Okay, proton number, very straightforward, very simple, means the number of protons in an atom. Okay, then after that we have your nucleon number. Okay, so what is a nucleon number? Nucleon number here What do we mean by a nucleon number? Nucleon number is the number of nucleons which we have in an atom. Okay, and like I mentioned earlier, what do we have inside the nucleus? We have protons and neutrons inside the nucleus. Okay, hence we say that the number of nucleons, in majority of places you will find the number of protons plus neutrons in an atom. Okay, now you also come across words like for the nucleon number we also use mass number. For the proton number, however, we use atomic number as well. Alright, all good? Now, over here let's talk a little bit about these subatomic particles one more time. The proton, neutron and the electron, the relative charges they have, and we'll talk about the masses which we have here for each of them. Okay, so first if we talk about a proton, now proton has a positive 1 charge. Okay, if we talk about a neutron here, like I mentioned, it is neutral, so it has no charge. Okay, and finally we've got your electrons here which have a negative 1 charge. Okay, then so this here represents the charges we have, and this here represents the relative mass. Okay, so a proton relatively has 1. Okay, for neutron we also consider 1. Okay, they're more or less the same. For the electron, however, it's very, very tiny. 1/1840. Okay, alright, so that way you can actually guess how small your electrons are. Right, so this is the reason why we say, whenever we talk about the whole structure of an atom, right, we say that your nucleus here, right, this part is the one where you have the entire mass concentrated. Okay, all right, because electrons really don't have much of a mass that we really consider them something. Okay, all right, next up we're going to talk about isotopes. So I'm sure you already know what isotopes are from your chemistry lessons, but we're just going to go over this anyways. So isotopes of an atom, or isotopes are atoms of the same element which have different number of neutrons or different nucleon numbers, right? So for example, we have a few naturally occurring isotopes out there, like hydrogen, right? For example, hydrogen, which you'd find like this. Okay, you would find carbon like this, carbon 12 and carbon 14. Okay, so let's study about these guys a little bit. Okay, now first, what is the proton number? Right, let's talk about that. Right, so the proton number over here, as you can see, is the same. It's not changing. Okay, so the number of protons that you have here is 1 for each of them. Okay, even in this case, the number of protons that we have here is 6. Okay, but what's different about them is this one. Okay, this number here is what's different. The nucleon number is different here. Okay, now what does that mean? Now, what exactly is the nucleon number? Right, so the nucleon number basically consists of the proton number, right, the protons plus the neutrons, right, protons plus the neutrons. Okay, right, so over here what is the nucleon number? The nucleon number is, let's say if we talk about this guy, it's 3. Proton number is 1. That means, what am I left with? The number of nucleons, right? Sorry, the number of neutrons. Okay, so the number of neutrons in this case is 3 minus 1, which is 2. So in this case, how many neutrons do we have? 2. In this case, how many neutrons do we have? 1. In this case, how many neutrons do we have? 0. Yeah, let's talk about that. The other one. This example, how many neutrons do we have? 12 minus 6, 6. How many neutrons do we have here? 14 minus 6, which is 8. Alright, okay. So here, this is what it means to have isotopes. Okay, as you can see, we have different number of neutrons. Okay, different number of neutrons. Alright, but they all have the same proton number. For this hydrogen, right, as you can see, we have the same number of protons. Okay, all right. So now over here, I mean, the chemical properties, once again, they are alike. They are very similar in all the aspects that we have. Okay, but the two main differences that we will be talking about over here. Number one is that we have non-radioactive isotopes. Okay, and then we have radioactive isotopes. Okay, so what exactly are non-radioactive and radioactive? Let's dive into that a little bit. Okay, so first we have the good guys. These are non-radioactive isotopes. Okay, and then we have the bad guys, which are the radioactive isotopes. So what does this mean, and what does this mean for this whole chapter, and how is it really linked? Let's talk about that. Okay, so non-radioactive isotopes are those which which are stable atoms. Okay, they do not emit any type of radiation, and they're just good guys. Okay, they're not harmful, they're not going to break down or anything like that. Okay, but if we talk about radioactive isotopes, okay, these isotopes, these are the ones which are unstable. Okay, and they do break down, giving out or giving off radiation. So let's do a quick example for that, to further build on it. Right, so for example, here I have my nucleus. Right, now the nucleus is, it's filled with neutrons. Right, so for example, these are neutrons, and as you know, it's filled with protons as well. Right, so when you see something like this inside a nucleus, right, when the number of protons is a little too much, yeah, what will happen? Right, as you know, since these protons are all positively charged, they would wanna escape, they would wanna repel each other, they would wanna fight each other. Okay, so when that number goes up, right, as the isotope starts getting bigger and bigger, right, the stability of it becomes more compromised. Okay, the more the protons we have, right, the more repulsion you're gonna have between the protons inside your nucleus. Okay, all right, and there comes a point when when the nucleus is going to break down. Okay, and what it's going to do is it's going to want to remove some of the guys or kick some of those guys out. Okay, so just imagine yourself in a room full of people, right, and that room has I'm assuming you're a guy, and there are a lot of guys in that room. Okay, now what would one do? That room is full of people, and it's just very congested, it's very difficult for you to breathe and walk. So what happens? You would want to kick a few guys out, if I'm being honest. Yeah, you'd want to kick a few guys out. You'd be like, okay, please get out of here, man. Right? That is what we mean by radioactivity. Okay, as soon as those guys are kicked out, there's more room there, there's more space. Yeah, so it's going to be a more convenient, for you to be there, right? So that's what we mean by non-radioactive and radioactive isotopes. Non-radioactive isotopes are the one where where the number of protons are in less number. Okay, so they're stable, they're not going to kick anyone out. Okay, they're happy where they are, right? Radioactive isotopes, on the other hand, are ones where these are the unstable ones, right? There are a lot of protons, okay, and they just don't want to be together. They would rather kick some of those guys out. Okay, now this whole kicking out of the room is, or this whole breaking down of the room, is what we call as radiation. Okay, so non-radioactive isotopes are the ones which are which are stable atoms. Oops, these are the ones which are stable atoms, and they don't emit radiation, although these guys here are unstable atoms and they do emit radiation, which we will further talk about. Okay, all right. Now, so this is linked with the other part which we're going to talk about. Okay, so what exactly is radioactivity? Okay, so radioactivity, I want you guys to make sure that you remember it. Okay, the words that I'm using here. Okay, this is tested quite a few times in the exam, so if you're good to go on the definitions, you can easily get your score there. All right, so what is radioactivity? Radioactivity is the spontaneous and random emission of radiation from unstable nuclei. Okay, I'm going to quickly write that down for you as well. So what is radioactivity? Radioactivity is the spontaneous and random emission of radiation from unstable nuclei. When do we have unstable nuclei? When we have these radioactive isotopes, right? When we have something like this going on, right? This is what we mean by unstable nuclei. You know what this is, right? This is the nucleus, also called as the nuclei. Okay, right? So the question is, you might get a follow-up question on this, that why does it emit particles, right? Why does it emit radiation? Why does it emit energy? So the answer to that would be so that it becomes stable, right? Previously, what was it? It was unstable, right? What is it trying to achieve? It's trying to achieve stability. All right, now, so that's what radioactivity is, right? That's what radioactive decay is. That it's the spontaneous and random emission of your of radiation from unstable nuclei. Right, now, what do we mean by spontaneous and random? Let's dive in that part a little bit. Okay, so spontaneous means that radioactivity or this emission can take place, and it's not affected by anything externally, like any external factors like temperature change, or electric change, or magnetic field, or pressure will not have any impact at the rate at which, or at the radioactivity, or at the emission at all. Okay, so it's free of that. Okay, so any changes in temperature, any change in pressure, any external factor whatsoever, right, it will not be affected by that, right? Similarly, what do we mean by random over here? What do we mean by random decay? it means that can randomly take place over space and time. It means that it does not have a specific time when it's going to happen. Okay, it is really impossible for us to say when a particular nucleus is going to decay. Okay, so that's what these two words means. All right, spontaneous decay and random decay. Okay, all right. Now, moving on. Over here, I've mentioned these three terms: alpha, beta, and gamma. Okay, these three are the types of radiation which we are going to be studying. Okay, there's alpha particles, there's beta particle, and there's gamma rays. Okay, we're going to talk about their natures, they're going to talk about their charges, the ionizing power, and all these different features that we have. Okay, now, all right, now, so followed by that, we have this thing called as radioactive decay. Okay, now what is radioactive decay? Like I mentioned earlier, we have three types of radioactivity. Okay, we have alpha decay, we have beta decay, and then finally we've got your gamma decay. All right, or gamma emission, I would say. Okay, now for radioactive decay, once again, it is whenever an unstable nuclei is shedding or is kicking out some of its nuclei to become more stable, right? That's what we mean by radioactive decay, right? And the way this happens is like I mentioned previously. For example, if this guy over here is unstable, what it's going to do is it's going to shed some portion of it outside. Okay, this is just a general representation of what we mean. Okay, now this one I'm going to call as the mother nuclei in the start. Okay, what happens is the mother nuclei or the parent nuclei, right? This guy is going to now turn or now give you a daughter nuclei. All right, so the mother nuclei is going to turn into the daughter nuclei. All right, and right here we have this tiny particles which we call as your decay products. So for the daughter nuclei, so previously we had the mother nuclei, right? It would just go down in size a little bit, right? Because obviously it shed some of its portion here, right? Just bring it over here. Okay, then about the decay product, we would have something smaller, right? We would have something smaller here, which has now left the overall system. Okay, so this is what we mean by radioactive decay, and this is what really happens. So mother or parent nuclei would probably turn into a daughter nuclei, all right? Then it would decay off, or it would emit some of its particles, which we call as decay products. Okay, all right, now these decay products can be either alpha, beta, or it can be gamma emission. All right, so for alpha decay, right, let's talk a little bit about that. For alpha, you're going to have, let's say, so alpha decay, right? So whenever you have an element, right, whenever you have a parent nuclei, and for example, if you talk about radium, sorry, 226, and the number here is going to be 88. Okay, now what happens? Let's recall. We had that big parent nucleide, right? It was breaking up into a smaller daughter nuclei plus that tiny particle, right? This tiny particle, if it's an alpha decay, right, that is going to be 4 2, which looks like a helium, or it's it's similar to a helium nucleus, right? Whenever there's alpha decay taking place, right, there is decrease in the nucleon number by a factor of 4, right? The proton number, how many protons leave? It kicks out 2 protons, okay, and it kicks out 2 neutrons. All right, okay, so whenever we have the alpha decay taking place, the element will now be short of 2 the proton number, okay, and the neutron number goes lower by a factor of 4, okay, and this is how an alpha particle is made. Okay, you can also represent this like something like this: 4 2. There you go. Okay, this is what we have here for an alpha particle. All right, now what are the remains? What's left? So out of 226, how much did we lose? We lost 4, right? So that's now going to turn into 222. Okay, how much of 88 did we lose? We lost 2, so that means it's now going to be 86, and this now turns into Rn, which is your radon. Okay, all right, so this is an example of a beta decay. What happens in beta decay? We have a loss of 2 in the proton number and a loss of 4 in the nucleon number. All right, moving on. The second type of decay that we have is your beta decay. Okay, we have your beta decay. In beta decay, once again, the process is very same. It's very similar. Okay, it's only the size of the particle, the nature of that is going to change. Okay, in this case, we have one high-speed electron which really leaves the system. Okay, we have one high-speed electron which is leaving. So I'll give you an example. Let's say we have iodine. Okay, 131 53. Okay, now what leaves from this guy? What is being kicked out? What's being kicked out is one electron. Also, you can write it down like this. Okay, all right, we'll talk about this in a bit detail as well afterwards. Okay, so this is what really leaves. Okay, now one thing I did not mention earlier, always remember whatever you have on the left hand side and whatever you've got on the right, right, they both have to be equal. In what sense? This is 226, which means this side should be equal to 226. This is 88, this should be equal to 88, which is the case. It's balanced in the first case. For the beta decay, what's really happening is there's one electron which leaves, right, which is written as a -1. Yeah, in this case, how we're going to write this thing? This will remain 131 since there's no neutron, but there's no proton leaving. Okay, however, what happens here is that this has to be now 54. Okay, this becomes 54 for it to balance, because over here we had 53, right? So over here it's 54 minus 1, which altogether gives you a 53. Now we're not just doing that just for the sake of balancing both sides. Okay, there's a reason why this happens. Okay, so whenever beta decay happens, right, there's one thing that that takes place inside the nucleus, which is that the neutron is going to change into a proton. Okay, what happens is that a neutron is going to change into a proton. Okay, so as the neutron changes into a proton, right, what will happen is that my proton number is going to increase, right? So similarly over here, my proton number is going to increase by 1 because it was previously 53. Now there's another proton, right? So it's now going to turn into 54, right? However, why? So I'm sure some of you might have a question that why doesn't the nucleon number, increase or decrease? So keep in mind, in the nucleon number, we have neutrons and we have protons. Okay, since one of the neutrons, as you can see, is going to decrease, one proton is also increasing right at the same time. Yes, so that is a dual effect, which is the reason why we don't have a change in the nucleon number altogether. Okay, so here we have your beta decay explained. All right. Okay, next. Lastly, we have this thing where we have gamma emission. Okay, now gamma emission is a little bit different. Okay, now what is gamma emission? Okay, now in this case, we don't have any particle as such which leaves the overall system. Okay, we don't have any particles, we don't have any mass which leaves the parent nuclei, right? In this case, so having said that, that means there's going to be no change in the proton number, no change in the nucleon number or anything like that. Why? Because no protons or no neutrons are in fact leaving, right? Nothing's leaving, it stays in its position only, right? But in some cases what happens is that without just kicking out the particles, there's one more thing that can happen. Right now in this case, as you can see, it's a big it's a big particle, right? What happens here is that this is too energized. Okay, this has too much of energy. Okay, it is having too much of energy. It has a high state. Okay, so what goes around over here? Why does why don't we have a change in the in the parent nuclide? Okay, that is because it exists in its energized state, or it exists in its excited state. Okay, it exists in its excited nuclear state. So rather what happens here is that once it emits gamma radiation, okay, gamma radiation would show like this, right? There's gamma radiation here, this is gamma ray. Okay, gamma ray leaves like this. Okay, you don't show anything over here. The symbol for it is something like this. There you go. Okay, all right. So this is what happens when you have a parent nuclei and it undergoes gamma emission. Now, previously, this this parent nuclei was excited, right? In this case, it won't be that much excited. Okay, it is just now going to be simply like this. Okay, so what does that mean for our equation? So for the equation, let's do a quick example. Let's say we have there you go, 234 91. Now this is what you'd find. You'd find a tight steric on top of it. Now this tight steric here, represents that this element here is in its excited state. Okay, now what happens when it goes under gamma emission? It will lose nothing in terms of the mass, right? No mass is going to go away. It's going to remain like that only. Rather, this was previously in its excited state. Now it's just not, because it has kicked out that excessive energy which was there. Okay? Alright? So here we have your gamma emission, alpha, beta, and your gamma emission. Okay, in the gamma emission, there's just this just gamma ray which leaves, which is is another electromagnetic wave that we have. Okay, once it leaves, um, your daughter nuclei is now free of that energy. Okay, the parent nuclei, which initially started off with more energy, is now more stable. Okay, all right, so here you can see a visual representation of what I was referring to. Here you have the parent nuclei, you've got the daughter nuclei, and you've got the alpha particle leaving. Similarly, you've got the parent, the daughter, and the beta particle leaving, and finally the gamma emission, where gamma rays leave and the daughter nuclei has less energy relatively if we compare it with the parent nucleide. Okay, right over here we've also written down the radiation which is emitted over here for beta and for gamma and for the alpha one. Okay, these here are the general equations we have. Okay, please write them down. Okay, and I think we should be good to go. It's very clear what really happens to the daughter nucleide. As you can see over here, 4 is subtracted, 2 is subtracted, nothing happens to A. There's a +1, right? Similarly, right here, there's no change in mass, and so on and so forth. Okay, these are the general equations we have for each decay that takes place. Alright, so right over here, as you can see, this is the Rutherford experiment I was talking about. Because of this experiment, we were able to, actually discover how exactly the nucleus works, how exactly, the nucleus is positioned. Alright, now let me just quickly pause this video here and talk about what apparatus or what arrangement was made. 1 second. Okay, so right here we have this source. This is the alpha particle source, okay, which means that we have a radioactive substance, okay, which has alpha particles, which is emitting alpha particles. Okay, right around it we've got this fluorescent screen, okay, and then we've got a very thin gold foil. Okay, now the purpose of this screen, of this lamina here, is to show exactly where the alpha particles are going to hit. Okay, and the purpose of this gold foil is to exactly test, or is to exactly figure out how an atom really looks like. Okay, and the reason that we're using a very thin gold foil is because we want to make sure that we have as less particles of gold as possible. Okay, now let's quickly go over the quick simulation here for alpha particles, how they leave that source. Okay, how they leave the lead box, the black box that you can see here. It's called, we use a lead box, L-E-A-D box. Lead is is an element here. We use lead because it is a good stopping material for all radioactive sources. Okay, now I'm going to further talk about that when we're doing our when we talk about the 3 different radioactivity in much more detail. Okay, now over here what really happens is that alright, let's see. Now these green tiny particles that you see, right, these are alpha particles which are leaving. Okay, now look very closely. As you can see, some of the particles are going completely straight without showing any deviation, although there are some particles here which show a little bit of deflection, right? And there are some particles here which are being turned back completely, right? Now let's talk about why this really happens. So this is what the gold atom looks like, right? Right in front of the center, you will see the nucleus, right? And outside the nucleus, there's this, there's this empty space, right? And around that, we have the electrons, which are basically orbiting around the nucleus. On the left hand side, you can see that we have an alpha particle, okay, which we are bombarding towards the gold foil or the gold atoms. Okay, now let's take another look at this and see what's going on. So here we have that, it's another way of looking at those gold foil, right? That gold foil here, this is the atoms which we're talking about now, right? Now we're gonna we're gonna leave the alpha particles now, all right? They're gonna come. Let's see what goes on here. The alpha particles are going straight, right? Majority of them are going straight. Why is that? That is because most of the part, or the majority part of an atom, as you can see, is empty, right? There are some of the alpha particles which are going straight but are a little bit deviated, right? Why are these deviated? There's some of them which are going straight, right? Some of them will deviate here. Okay, now why is that? Let's talk about that with a picture. Alright, so over here we have this structure of an atom. Okay, we've got the nucleus over here in the center, right? This part. Okay, this space here is empty. This is the the direction of travel we had for the alpha particles which we were bombarding from the source, right? As you can see, they're going straight, right? Some of them were going like this in this position, some of them were traveling like this, like this, like this, and like this, right? Now the first observation which was made was that the majority part of an atom is empty. Okay, now why was that? The reason for that was majority of the alpha particles went straight. They showed no deflection at all, right? They passed straight and they went to hit the screen at that point, right? The second point was made looking at this thing, right? You can see here, right? These are showing less deflection. Okay, there is less deflection over here for the alpha particles. Okay, what does that mean? It means since alpha particles are positively charged particles, right? Alpha particles have a positive charge on them. Yeah, so just because they're positively charged and just because the nucleus altogether is a positively charged body, right? That's the reason why we say that over here you have this tiny change, right? You have this tiny deflection. So why is there tiny deflection? The reason for this tiny deflection is perhaps because we might have another positive entity here, right? We might have another positive thing here, right? The reasons why the alpha particle over here is being deflected from here to here is because if this alpha particle is positively charged, this is also positively charged, right? So this is why we were able to detect that, okay, the central part of an atom here, right, it carries a positive charge. Okay, so first part here that we were able to tell, that was the fact that the major part of the atom is empty. The second part that we were able to say that over here, the center part or the central position over here for the atom, right, that carries a positive charge. Why? Because there was a small portion of particles, of alpha particles, which showed little deflection. Okay, and then the third one was that only a small fraction of particles showed complete deflection, right? Why was that? The reason for that is because the size of the nucleus is so small, right, that only some of the particles were turned back completely. Okay, if the size of the nucleus, for example, was something like this, would go back, right? And what would that mean? That would mean that the size of the nucleus is more. In this case, the size of the nucleus is small. That's why only small number of particles are being turned back. Make sense? So that is what the whole experiment was for, to help us figure out, to help us find the exact position or the exact structure of the atom. Okay.